Pluto, the baffling bantam planet living at the external scopes of our nearby planet group, is working up energy inside the cosmic community. Ongoing reports indicate a potential encounter with Neptune, raising concerns among researchers and space fans alike. Prestigious specialists, including Neil deGrasse Tyson and Miyoku, have sounded alarms about the likely results of this divine conflict. But how did Pluto end up on an impact course with its far-off neighbor? And what could this infinite crash mean for us here on Earth? Let us investigate this unfolding event. Once thought to be an undeniable planet, Pluto was subsequently renamed as a bantam planet due to its unique orbit. Regardless of this change, it continues to enrapture and engage space experts. Ongoing predictions from prominent researchers highlight a stressing nearness between Pluto's orbit and that of Neptune. These specialists warn against a possible impact between the two planets, posing a significant threat to Earth. Pluto's journey around the Sun is marked by its superior characteristics within our nearby planet group. Its orbit spans an impressive 248 years, and since its discovery in 1930, Pluto still hasn't completed a full revolution, adding to its intrigue. The exceptionally circular shape of its orbit is a departure from the nearly round orbits of the major planets. Moreover, Pluto's orbit is tilted at 17 degrees to the ecliptic plane, making its path steeper compared to other planets. One prominent feature of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, defying expectations based on their relative positions in the solar system. So why hasn't an impact occurred between Pluto and Neptune? The explanation lies in the gravitational forces exerted by other planets. The analysis of Pluto's orbit began shortly after its discovery, presenting an astounding challenge for cosmologists. Unlike most planets whose orbits align relatively close to the ecliptic plane, Pluto's unique features include a steep inclination and an eccentric orbit. The mystery deepened with the realization that Pluto's orbit crosses that of Neptune. The stability of Pluto's orbit amidst these complexities serves as evidence of the intricacies inherent in space mechanics. The three-body problem in space involves calculating the motion and gravitational interactions among three celestial bodies, such as Pluto, Neptune, and the Sun. This problem explains the complex interchange of their paths and gravitational forces. Terms like IML libration and the koi swaying help unravel this divine mystery. Astrophysicists argue that a vibration responsible for maintaining planets in their orbits plays a key role in the Pluto-Neptune system. This term means that when Pluto crosses Neptune's orbit, it is situated no less than 90 degrees away from Neptune, crucially preventing potential crashes. Libration ensures that when Pluto approaches Neptune or other giant planets, it is arranged predominantly above their orbital plane, offering an extra layer of protection against impacts. The koi sway explains why Pluto's orbit around the Sun appears irregular but remains stable over time despite apparent randomness in space. Mathematical simulations in the late 1980s revealed that despite its steady properties, Pluto's orbit is in reality chaotic, with slight initial deviations leading to significant changes over millions of years. However, Pluto's special orbit maintains stability over incredibly long timescales, keeping disorder within limits. Ongoing computer tests have enhanced our understanding of how large planets like Neptune, Jupiter, and Saturn affect Pluto's path around the Sun. Neptune's unique relationship with Pluto, completing 3 orbits for every 2 of Pluto, contributes to the stability of Pluto's orbit. Additionally, Jupiter's immense gravity exerts a substantial influence, while Saturn's influence, though smaller, also plays a role. Through extensive studies, researchers have shown that the combined effects of Neptune, Jupiter, and Saturn ensure the safe and stable movement of Pluto in space for billions of years. These phenomena are crucial for maintaining the order and consistency of celestial movements in the universe. Without these mechanisms, the solar system would be prone to greater chaos, potentially leading to impacts or ejections from stable orbits and causing widespread consequences for other celestial bodies. Understanding Pluto's orbit is particularly important in discussions about a potential crash with Neptune in the future. This knowledge offers a clearer understanding of the dynamic nature of the planetary system. Pluto's case highlights how seemingly unstable orbits can reach equilibrium through the complex interaction of gravitational forces and orbital mechanics. Continuous observation and investigation of these phenomena are vital for gaining a better grasp of our place in the universe. Exploring the depths of space often reveals the capricious nature of celestial bodies, and Pluto's orbit serves as a perfect example of this eccentricity. The concept of orbital disorder strikingly demonstrates the delicate dependence of a celestial body's path on its initial conditions. As illustrated in Pluto's case, even slight variations in the dwarf planet's position or speed can dramatically alter its long-term orbit. Programmatic simulations have been instrumental in helping researchers understand how Pluto moves in space. By making small adjustments to these simulations, space experts can observe how even minor changes can have a significant effect on Pluto's trajectory. In the late 1980s, these simulations uncovered a fascinating aspect of Pluto's orbit. Despite factors like IML and vibration contributing to its stability, Pluto's orbit can still display irregularity. Even a tiny initial difference in Pluto's position or speed can lead to major changes in its orbit over many years. Nonetheless, despite this inherent chaos, Pluto's orbit remains stable for an especially long time spanning billions of years. This suggests that beneath its seemingly erratic appearance, Pluto's journey around the Sun follows an organized order. Anticipating celestial events and predicting the future paths of celestial bodies, especially with planets like Pluto that have unusual orbits, is very challenging. The inherent unpredictability of these systems makes long-term predictions uncertain. Mathematical simulations help us understand and forecast the future motions of celestial bodies, but they also reveal the limits of our predictive capabilities. These models heavily rely on precise initial conditions and simulate complex interactions. Even a small error can lead to drastically different outcomes, making accurate predictions difficult. The chaotic nature of celestial orbits, such as Pluto's, reminds us of the ever-changing universe. While we've made progress in understanding space, Pluto's case highlights our ongoing limited knowledge. Understanding the gravitational impacts of giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates how the presence and position of each planet can affect the stability and direction of other bodies in the system. In spite of these intricate forces, prominent astrophysicists are expressing concerns about a potential impact between Pluto and Neptune. Neil deGrasse Tyson, a renowned astrophysicist, offers a unique perspective on the mysteries of our solar system, particularly regarding Pluto. Tyson, famous for renaming Pluto as a dwarf planet instead of a full-fledged planet, shares insightful thoughts on how our understanding of celestial mechanics is constantly evolving. Tyson views Pluto's renaming not as a downgrade but as a necessary adjustment in line with our growing knowledge about the various objects orbiting the Sun. His approach to celestial mechanics involves continuous learning and adaptation. He sees the complexities of orbits like Pluto's as a sign of how much more there is to discover in space. Tyson believes that the allure of these mysteries makes space science so fascinating. Additionally, Tyson is aware of how space-related events and discoveries capture the public's attention. He sees events like Pluto's renaming and its peculiar orbit as opportunities to engage the public's imagination and curiosity about the universe. By discussing the dynamic and sometimes illogical aspects of space mechanics, Tyson encourages a deeper understanding and enthusiasm for the cosmos. Neil deGrasse Tyson opens a window for the general public to wonder at the miracles and mysteries of the universe. Working alongside other researchers, Tyson actively warns the public about the potential risks of Pluto's unusual orbit. After extensive study of Pluto, he has raised concerns that the three-body problem could pose a serious threat, suggesting that a collision with Neptune may be long overdue. Furthermore, Tyson emphasizes how such a collision could disrupt the balance of the universe and lead to disastrous consequences extending even to Earth. A collision between Pluto and Neptune would be a rare and catastrophic event in our solar system. This crash would release a massive amount of energy, likely disintegrating Pluto due to its smaller size and cold composition. Debris from the collision could spread throughout the solar system, posing potential dangers to other planets and their moons. For Neptune, such an impact could potentially alter its atmosphere and orbit, depending on the specific details of the collision. Michio Kaku, a famous theoretical physicist known for his work in string theory and science communication, offers an intriguing perspective on this scenario. His views on the future of space exploration and the connection between celestial mechanics and theoretical physics provide deep insights into phenomena like Pluto's orbit. Koku sees the study of Pluto and its orbit as a glimpse into the future of space exploration. Understanding the complex gravitational interactions and orbital elements of celestial bodies like Pluto, according to Koku, can offer critical insights for future space missions. This knowledge can help in navigating the solar system more effectively, anticipating potential risks, and planning missions to the outer reaches of our planetary system and beyond. Koku stresses that the lessons learned from studying Pluto's orbit can be applied to exploring other celestial bodies, providing a blueprint for approaching and understanding distant worlds. In discussing the physics of planets, Koku often highlights the profound connection between celestial mechanics and theoretical physics. He believes that the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are not isolated events but are tied to fundamental principles of physics. Koku's work in theoretical physics, particularly in string theory, aims to grasp these principles at the most fundamental level. He proposes that considering the complexities of celestial mechanics like Pluto's orbit can yield insights into the fundamental laws of the universe. Like Tyson, Koku has also addressed the potential collision, relating it to his theories about the cosmos. If Pluto and Neptune were to collide, it would be a significant event in astronomy, providing a unique observational opportunity that could potentially contribute to our understanding of string theory. String theory, a theoretical framework that replaces point-like particles with one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. The impact of such a magnitude in the solar system could create extreme conditions of energy and gravity, offering insights into the behavior of fundamental particles and forces under extreme circumstances, a key focus in string theory. Also, the gravitational waves produced by the impact could provide valuable data for testing predictions of string theory related to gravity and space-time. While the direct impact on Earth would be negligible due to our distance from the outer solar system, the scientific implications of such an event could be significant, potentially contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's orbit serves as a significant example of celestial mechanics, demonstrating both stability and chaos within our solar system. The extraordinary features of its orbit, influenced by the gravitational forces of neighboring planets, especially Neptune, highlight the intricate and dynamic nature of space. The universe holds numerous secrets, and the three-body problem is just one of them. There are other potential catastrophes that scientists anticipate. While the chances of planets colliding in space are very low, it is not entirely impossible. The way planets' orbits are influenced by various factors, including gravitational interactions, is explained by the three-body problem. In some space systems like TRAPPIST-1, with 7 Earth-sized planets, gravitational forces create a rhythmic pattern called orbital resonances. Over time, these patterns can make planetary paths less stable, potentially leading to collisions. Despite the crowded nature of systems like TRAPPIST-1, impacts are not currently happening. Researchers closely monitor these systems to understand how planets affect each other's paths, especially when they are close together. This information helps us understand the movement of planets in space. Maverick planets drifting through space without orbiting a star present an additional curious element. These planets, once part of a star system, are ejected due to gravitational disturbances or other cosmic events. For example, the close approach of another star or dynamic instability in other systems can cause these rogue planets to travel vast distances, potentially reaching areas far from their origin. During their lone journey, there is a possibility of them encountering another star system. If one of these rogue planets enters another nearby planetary group, there is a slight chance of a collision with a planet in that system. However, given the vast and mostly empty nature of space, the likelihood of a rogue planet directly impacting another planet is extremely low.